Okay, so the next operation we're going to consider is set difference. So let's take an example of two sets. This time let's take the set A to contain the elements A, B, C, and D. And we'll take the set B containing the elements A and B. Okay, so we've two ways we can form the set difference here between these two sets. Let's consider the first one to be A difference B. And then we'll go on to have a look at B difference A. So for A difference B, we want to have a look at the set A and remove any of the elements from the set A that are also in the set B. So in this case, A difference B is going to be the set. Okay, so let's have a look first. We have A an element of B, A is also an element of A. So this is a candidate for removal. The next element in B is the element B, and we can see that B is also an element of A. So this too is a candidate for removal. So let's remove from the set A the elements A and B. The resultant set from that operation will be the difference. So removing the elements A and B from A will leave us with the elements C and D. So C and D are the elements in the resultant set A difference B. Next, let's have a look at B difference A. Okay, so this time we want to have a look at all of the elements of A, and if any of them are also in B, we want to remove them. So straight away, let's have a look at the first element of A. Well, the first element of A is lowercase a, and we can see that that is also an element of B. So we want to remove it from the resultant set. The next element in A is lowercase b, and we can see that this element is also an element of the set B, so we want to remove that. Now when it comes to the final elements of the set A, we've got C and D. These don't appear anywhere in the set B, so we can't remove them. So the result of B difference A is that we've removed the elements A and B from the set B, and we're left with the empty set, or the null set. So from this we can see that A difference B is not equal to B difference A, generally. Okay, so let's move on then and have a quick look at the idea of disjoint sets that we encountered. So recall, two sets are said to be disjoint if they have no elements in common. So let's take two sets then. A equals set with elements A and B, and B is the set with elements 1, 2, and A. Okay, so let's form the intersection then. So A intersection B, in this case, we're looking for the common elements between the two, is solely the element A. So in this case, A and B are not disjoint sets. Okay, so let's have a look then at another example. This time let's take A to be the set, again with elements A and B, and B to be the set with elements 1 and 2. Let's form the intersection again. So A intersection B, in this case, we're looking for the common elements between the two of them. None exist. So in this case, we have the empty set as the resultant set. So if the intersection of two sets results in the empty set, we say that these sets are then disjoint. In the first case, not disjoint. Okay, so let's do some more examples with the final operations that we saw. One of them was the complement operation, and the final one was symmetric difference. So when we're dealing with the complement, we saw that we involve the universal set. So the universal set is going to be a given set of all of the elements that we're interested in for a given problem, typically denoted using a capital U. So let me say that my universal set for this problem I'm interested in is the set with elements 1, 2, 3, 4, 5, and 6. And we want to take another set of elements that are going to be a subset of this universal set. So let's take the set A. And let's say the set A contains the elements 1, 2, 3, and 4. Okay, and we can see here that A is a subset of the universal set. So let's form the complement of A then. So the notation we've used is A dash. And sometimes you may see this written as A with a capital C. And the complement is going to be defined as the universal set less the set we're interested in. So in this case, we've seen the difference operation already. Let's have a look at how it works out with this example. So we want to have a look at the set A. Any of the elements that are in A that are also in the set U, we want to remove them. So in this case, we're going to end up with, well, let's have a look. 1 is an element of A and also of the universal set. So that will be removed from the universal set in order to get the resultant set. 2 is an element of A and also of the universal set. 3 is an element of A and also of the universal set. 4 is an element of A and also of the universal set. And that's what we expect, because we've seen that A is a subset of the universal set. So removing the elements 1, 2, 3, and 4 from the universal set, we are then left with the set of elements 5 and 6. So in this case, the complement of A is the set with elements 5 and 6. Okay, finally let's have a look at the symmetric difference operator. So let's take two sets again. This time we'll define the set A to be the elements 1, 2, 3, 4, and 5, and the set B to be the set with elements 2, 3, 5, 6, and 7. So let's form the symmetric difference. Okay, and we write this as A. We use the triangle symbol for the operator, B. The idea with symmetric difference is we want to find all of the elements that are in A and all of the elements that are in B and remove any of the elements that are in both A and B. Okay, so let's scan across. We know that the elements that are in both A and B are essentially the intersection of A and B. So we know that we want to remove the intersection of the elements. So let me put that in first. And we want to remove the intersection of the elements from the complete set of all of the elements that are before us. Okay, so to get the complete set of elements from A and B, that would be the union operation. So this is one formulation of the set difference operator. First of all, form the union of the two sets, and then from that resultant set, remove any elements that are in the intersection of the two sets. So in this case, A union B would be the set 1, 2, 3, 4, 5. 2, 3, and 5 are already listed, and then we have 6, and 7 also. And then we want to have a look at the intersection. So the intersection of the sets A and B are the common elements between them. And in this case we see that the intersection consists of the elements 2, 3 and 5. Okay, so we've formed the union, we've formed the intersection. We now need to apply the difference operation between those two sets. Okay, so remember the difference operation will remove from the set on the left-hand side of the operator all of the elements that are contained on the right-hand side set of the operator. So in this case, we want to remove the elements 2, 3 and 5 from the set here, the union. So the resultant set then would be 1, 4, 6 and 7. Okay, another way to think of the symmetric difference operator is in the following way. So A symmetric difference B. Well, first of all, let's say we have the set A. Let's remove any of the elements from the set A that are in the set B. So that would give us A less B. And then we want to consider it the other way around. We want to take all of the elements in set B and take away all of the elements that were in the set A. So we want to union that with all of the elements from B and get rid of all of those that were already in A. So let's work this out and we should get a corresponding answer. So A less B. Okay, so remember, look at the elements of A and remove any that are also in B. So this results in the set 1 and 4. Union. And now let's have a look at the difference B difference A. So this time we're looking at the set B and removing any elements that are in the set A. So in this case, the result will be 6 and 7. And then we union those two sets together. The resultant set will be 1, 4, 6 and 7. Okay, and we can see that the first way we did it corresponds with the second way we did it.